Okay, grade 8. This is the last part of our algebra chapter on how to learn how to solve algebraic equations using opposite operations. So the 4 questions we've done here for the warm-up ask you to first model to solve it and then solve them by opposite operation. Okay? I don't know why that's doing that, but anyway. So the first question is this picture here. So if I was to interpret it, it says x and a negative 5 or minus 5 is equal to negative 10. So when we have equations, the first thing we should always try and do is we always have the idea in our mind that we're trying to isolate the variable or get x by itself. So in this particular equation, we realize that on the side that has the variable, the x here, there is 5 negatives. And through our understanding of opposite operation and integer sense, we knew that if we put positive 5 with a negative 5, that will create a 0 pair, and I'll be left with x. But what we also learned in the last couple days through modeling is that whatever I do to one side of an algebraic equation, I have to do the same thing. So since I put positive 5 on that side, I have to put positive 5 on this side. And in doing so, the negative 10 that was there now becomes a negative 5, and I have the solution x is equal to negative 5. Now the second thing asks you to then take that and then do it numerically instead of through modeling. So if it says x minus 5 equals 10, I have to ask myself, what is the opposite of taking away 5? And the answer to that, the opposite is adding 5. So I'm going to add 5 to both sides, and this is exactly what I want it to look like on your paper. Underneath the constant, you have put a plus 5 instead of the minus 5. And what you're going to do is you're going to draw a line through those two to show that you understand those are opposite operations. And what you're left with is an x. This line that I put through is the exact same thing as the line we kind of put through all of those 0 pairs there, right? And over here, when I combine a negative 10 and a positive 5, I end up with a negative 5 in the same way I did over here. Okay? So in both cases, this is the work you would show me for modeling. This is the work you would show me for opposite operation. And in both cases, I end up with the same solution, x as a value of negative 5. In the second example, if I interpret it, instead of having all of x here, what I have is, again, just like we did in the last video, I have a third of x. So a third of x, the easiest way to write a third of x is like that. And we have a negative 1, which is right here, is equal to negative 3. Okay. So in this particular equation, we have a constant. Our constant's negative 1, and as we said before, the first thing you should always do is get rid of your constant. So from a modeling, I'm going to put a plus 1 on this side, or a positive 1, and I'm going to do the same thing to the other side. When I do that, my next picture is going to be a third of x is equal to negative 2. Now I'm going to switch over to the other side just for a second to do opposite operation. What I did there was I added 1 to both sides. That's a 0 pair. I'm left with a third of x is equal to negative 2. So at this point, we're at the same spot in both our modeling and in our opposite operation. And our ultimate goal is not to know what a third of x is, but what x is equal to. So I'm going to bring this down just a bit here. I'm going to ask myself the question, how many of these do I need to make a full x? And the answer is I need 3 of them. So what I'm going to do is I'm going to triple this side from a modeling perspective. And if I triple one side of a scale, I must triple the other side. And these 3 thirds, is that a siren? It sounds like a siren. Those 3 thirds of x are going to make x equals negative 6. My answer or my solution will be x is equal to negative 6. Negative 6. Over here, since I tripled this side here, numerically, tripling a side means multiplying by 3, and I'm going to show it like this. Bracket 3 for multiplication. We're not going to use a multiplication symbol because it looks too close to the x. And I'm going to put a line through those to show that dividing by 3 and multiplying by 3 are opposite operations, or tripling a third of something will give you the thing that you're tripled. And the product of -2 and positive 3 is -6. So in both cases, I end up with the correct solution. The same solution of x is equivalent to -6. In the third example, I have 2 as my constant. Now, normally our constant goes second in our expression, but this time it goes first, no big deal. So this says 2 and a negative x or a minus x is equal to -4. So the equation that's pictured there is 2 and a negative x equals -4. So the first thing from a modeling is I'm going to get rid of that constant by putting -2 on both sides. And that is going to leave me with a negative x is equal to -6. And the opposite of x is equal to 6, so therefore x itself is equal to positive 6. And therefore x is equal to 6. Now, this is one of those things that doesn't look the same when I do it algebraically using opposite operation. So the first thing I did, if you remember, is I put -2 on both sides. So here, if I put a -2 on both sides, that gets rid of the constant of positive 2. Now, some people look at this and think that that is a -2, and they put a +2 on both sides. But that's wrong, because that's sugar. Because that is not a part of the 2, that's a part of the x. That's a negative x. So it's a positive 2. I'm going to subtract 2 from both sides. Now look what's left. It's a negative x is equal to -6. Now here's where it gets interesting. I haven't talked about this yet. It's the first time I'm going to talk about it. In front of x, for example, what is the coefficient in front of x? It's 1. We never write coefficients of 1 because we know that x is just one of them. Now, what is the coefficient in front of a negative x? It's actually a -1x, okay? Now again, just like we don't write a 1 coefficient, we don't write a -1 coefficient. But if I was trying to get rid of, let's just say for example, a 2x, I would divide both sides by the coefficient, and that would leave me with x. If it was a -2x, I would divide both sides by -2, and it leave me with x. Now, if it was a negative x, what would I divide both sides by to get rid of the negative symbol? I would divide by a -1. Agreed? Because that's what the coefficient is. So because that's the coefficient, here's what you do at this step. Now make a note of this because I don't think anyone did it. I want you to divide both sides by -1. And I want you to put a line through there, and I want you to leave yourself with a positive x. And then I want you to say, what is -6 divided by -1? It's positive 6. And your last question gives you this. If I interpret it, it's 3x minus, or plus 4, excuse me, equals -2. So the first thing I'm going to do is add -4 to both sides to get rid of my constant. That leaves me with an x, an x, and an x equals -6. Since 3x is equal to -6, then each of these x's must be equal to -2, and therefore x is equal to -2. If 3x is equal to -6, then each x must be -2. Now from an opposite operation standpoint, I'm going to subtract 4 from both sides. I'm going to put a line through that to show that I got rid of my constant in the same way that I put lines over here, leaving me with 3x equals -6. I then took this and I divided it into 3 scales. So here I'm going to divide both sides by the coefficient of 3, which is opposite to multiplying by 3, leaving me with x equals what -6 divided by 3 is, which is